Welcome to Chapter 16 of And So Squircle. Today, I'll be showing two super sweet integral types that involve base p trig. The first type is the integral of the absolute value of cosine base p to the p and sine base p to the p, integrated along their periods, both of which are pi due to the absolute value. To be completely clear, the big P on these integrals is shorthand for any interval of length pi. It would be the same as integrating from any value x to x plus pi. We'll start by defining a function I to be the cosine integral. As a side note, we'll be treating little p as a constant throughout this video. Using the second fundamental theorem of calculus, we can show that I prime is the integrand of I evaluated at x plus pi minus the same thing evaluated at x. And since the period is pi, this is equal to cosine minus cosine, which of course is 0. Since the derivative of I is 0, then I itself must be a constant function, which means that I has the same value no matter what is inputted. Similarly, if we define a function j to be the sine integral, we can show that j too must be a constant function. Now let's let u equal t plus pi over 2. Using this, we can take j and rewrite it as an integral with cosine instead. If we put the definition of I up on the screen, we can see that this integral is equal to I of x plus pi over 2. Additionally, since we know that I is a constant function, I of x plus pi over 2 is equal to I of x. So we've shown that j and I are actually equal. Now, if we recall the Pythagorean identity and integrate both sides, we can show that I of x plus j of x is equal to pi. And since j equals I, we can combine the two, leaving us with I equals pi over 2. And once again, using the fact that the integrals are equal, we can end with that the cosine integral is equal to the sine integral along their periods, and that value is pi over 2. Or maybe in an easier form to remember, these integrals from 0 to pi are equal to pi over 2. Next, we have some similar integrals, but instead of to the p, we're squared. Here, the big P still represents an interval of length pi. We're going to work with these integrals in a very similar way as with the last two. We'll let a function I be defined as the cosine integral, and using the fundamental theorem of calculus, show that it's constant with respect to x. We'll do the same with j. Doing the same use up as before, we can get that j of x is equal to I of x plus pi over 2, which, since I is constant, is equal to I of x. Now we can recall that cos base p squared plus sine base p squared equals height base p squared, and integrate both sides of this equation along p. This is equal to I of x plus j of x, both of which we know are equal, so I of x is equal to 1/2 the integral of height squared along a pi-sized interval. So at this point, we have these three integrals being equal to each other. However, we can go further if we take a look at the height integral. Since any interval of size pi works, we can write the bounds from 0 to pi using theta here in the integrand to better illustrate what this integral represents. We can see this integral as the polar form of half of a squircle's area, with our r being height base p of theta. Rewriting this in Cartesian coordinates, we get this integral, which represents the area of the top half of a squircle, which, funnily enough, there is a formula for this in terms of the beta function. So here we have the two integral types, and for those who can see what I might be going for with regards to how I oriented the equations on the screen, we can make these more symmetrical by filling in these gaps with, albeit less interesting information. But these are the super cool and simpler versions, and that's it. Bye! Wait, I mean, we also have this, but...